It is compulsory. I have started the recording.
This
I
call is
thought
now being recorded.
Thank you, sir.
I have started the recording. Thank you very much to bring it to my notice. Shall I go ahead?
Sir, yes, sir. Yes, sir. Recording
I
is
hope,
on.
I hope you are understand. I hope you are able to understand the stuff which I am going through.
Yes, sir.
Okay. So, so what we do when we talk about the first order of field scheme, we assign a value of upstream cell center to the face of the control volume. So phi f is always equal to phi u. When the flow is in positive x direction, this phi f will be phi p. When it is in negative x direction, phi f will be phi e. So similar to this FOU, there are other extrapolation schemes also, and there are two interpolation schemes which are popularly used in all the softwares. The first order upwind scheme involves one upstream cell center value. Similar to that, there is a second order upwind scheme which involves two upstream cell center values. And in the interpolation, what we do first is the central difference scheme, which involves one downstream and one upstream cell center values. And there is another interpolation scheme called quick, which involves which quick is nothing but it's a quadratic upwind interpolation for convective kinematics, which involves one downstream and two upstream cell center values. We will look into all these convection schemes one by one. So for the derivation of a convection scheme, for the derivation of expression to determine the value of variable on the face of the control volume, we will derive some expression. For that derivation, we will make some assumptions now. We will make some notations. We will change the notations which we were using so far. So for the sake of understanding, we will always consider the east face. So my phi f will be always equal to phi e. We will be doing it for the east face. We'll try to understand the equations or expressions for determining the value of phi small e. So if this is the east face, this is my cell center under consideration. This is my cell center, east neighboring cell center. This is west neighboring cell center, and this is west neighboring cell center, and this is east neighboring cell center. So if I want to determine the value of variable on east face, this east neighboring cell center will now be called phi d if my flow is occurring in positive x direction. So this will be phi u, that is upstream cell center, phi at upstream cell center when my flow is occurring in positive x direction. And this is phi uu when my flow is occurring in positive x direction. Similarly, when my flow is occurring in negative x direction, I'm still trying to find out the value of variable on east face, then phi p will be equal to phi d. Phi capital E will be phi u, and phi capital EE will be phi uu. The same expressions are written here. I hope you understand that. So we have simply changed the nomenclature from phi p, phi e, phi w to that of phi d, phi u, or phi uu, and so on and so forth. Let us look at the second order upwind scheme, that is SOU. For this SOU, what we do, we adopt linear extrapolation. So second order upwind scheme is the extrapolation scheme. Let us assume that I'm interested to find out value of variable on east face. So this becomes my upstream, this is upstream, and this is downstream if my flow is occurring in positive x direction. So I assume that my x starts from here. I assume that my x starts from here. Then at x equal to 0, I have phi is equal to phi uu, and that gives me b is equal to phi uu. If I use phi is equal to ax plus b. At x equal to delta x, I have phi is equal to phi u. So that gives me a is equal to phi u minus phi uu upon delta x. So if I put this value of a and b in the expression here, I obtain the expression for phi as phi u minus phi uu upon delta x into x plus phi uu. Now I am interested to find out the value of phi at east face, which is at a distance of delta x and half delta x, that is at a distance of 3 by 2 delta x. So phi e at a which is at a distance of x equal to 3 delta x by 2, I can replace this x by 3 delta x by 2, and what I obtained is 3u minus phi u divided by 2 as an expression for phi e. So now my phi e is expressed in terms of cell center value. But this is the extrapolation. I have used two upstream values to determine the value of phi e. So this phi e is required to be determined. Once I determine this phi e, I can calculate the convection across this east face. How do I calculate convection across this face? I know the expression, that is CP east face can be, I know the mass flux across that east face. Now I know the value of phi e. I know the value of delta SE. So I can calculate the convection across east face. Similarly, I can do it for west face, north face, south face, and so on. Of course, we need to decide whether I'm going to use a second order of wind scheme or not. The next important scheme is a quick quadratic interpolation. SOU is extrapolation, but this is interpolation. Here, it involves one downstream and two upstream values. And we use the quadratic equation for phi is equal to ax square plus bx plus c. X equal to 0, phi is equal to phi uu. That gives me phi is equal to phi uu. At x equal to 0, phi is equal to phi uu. That gives me c is equal to phi uu. And then I have other two conditions now. At x equal to delta x, phi is phi u, and at x equal to 2 delta x, phi is equal to phi d. If I use these two conditions, what I obtained the values for a and b. So this is the value of a, this is the value of b. And now I want to find out the value of phi e, which is at a distance of delta x plus half delta x, that is 3 by 2 delta x. So phi e, which is at a distance of x equal to 3 by 2 delta x, I obtain the expression in terms of cell center values, that is phi d, phi u, and phi uu. This is my expression for quick convection scheme to determine the value of variable on the east face. Now, how to implement these convection schemes in the code? That is an important part, because a priori I do not know the direction of the flow. If I don't know the direction of the flow, how do I implement? I mean, which cell center shall I consider as upstream and which cell center I shall consider as the downstream one? So that can be taken care by using functions like maximum, library functions like maximum of the two values. For example, here I'm sharing with you the convection implementation of convection FOU convection scheme, that is first order upwind convection scheme. My expression is convection flux is equal to FME phi E. This phi E is always equal to phi u for first order convection scheme. Now, when my flow is occurring in positive x direction, my phi p is phi u. When it is occurring in negative x direction, my phi capital E is phi u. So which value shall I use? Whether I shall use phi p or phi e? Phi p is to be used when my flow is in positive x direction. Phi e is to be used when my flow is in negative x direction. So what I do, I write an expression like this: maximum of FME, comma 0 into phi p minus maximum of minus FME, comma 0 into phi e. Now look, when my flow is in positive x direction, which one will be maximum among these two? FME will be maximum among the two. And here 0 will be maximum. So because 0 is maximum, this term will be automatically omitted and phi p will be retained. When my flow is occurring in negative x direction, between FME and 0, 0 will be maximum. And this term will be omitted. And minus FME into FM minus, this becomes positive. So this term will be maximum and hence this term will be retained and hence phi will be retained. So when the flow is in positive, x direction, this term is retained. When the flow is in negative x direction, this term will be retained. So thus I can implement first order of wind scheme to calculate FCE. So FCF is FMF into phi f into FMF into phi u. So phi u is either phi p or phi e, depending on the direction of the flow. The same thing I can. For central difference scheme is a central difference scheme is simple. We take it's an interpolation scheme. We take the average of the two, that is upstream and downstream. So even if the direction changes, the upstream and downstream will be exchanged, but the average of the two is always required to be taken. So we need not to bother about the implementation of a central difference scheme. It's straightforward. FCE is equal to FME into phi, that is equal to FME into phi p plus phi e divided by 2. If the flow, even if the flow is positive or negative, it is always going to be phi e plus phi p divided by 2. That is phi u plus phi d divided by 2. When it comes to second order of wind scheme, the equation is FCE is equal to FME into phi e. That is FME. This phi e is to be determined using the expression which we have derived: 3 by 2 phi u minus 1 by 2 phi u. Now this phi u, when it is occurring in the positive direction, it is phi p, and phi u is phi w. Phi p and phi w. But when the flow is occurring in negative x direction, my phi u is phi capital E and phi u is phi capital E. So I can again use the same methodology as we discussed in FOU. Maximum of FME, comma 0. When the flow is occurring in positive x direction, this term will be retained. When the flow is occurring in negative x direction, this term will be retained and this term will be omitted. The same thing we can do for quick convection scheme. The expression is for quick convection scheme, we have derived the expression already. This is the expression: 3 by 8 of phi d, 6 by 8 of phi u, and 1 by 8 of phi uu. 6 by 8 is converted to 3 by 4. That's it. So when my flow is occurring in positive x direction, this term will be written. Now phi d is phi e. If it is the positive x direction, the flow is occurring in positive x direction, my phi d is phi capital E. Phi u is phi capital P, and phi uu is phi capital W. When the flow is occurring in negative x direction, my phi d is phi p. See here, phi d is phi p. My phi u is phi e, and phi uu is phi e. This is phi e. And then again, I can use the library function maximum to obtain to omit one of the terms and retain one of the terms. So this is the implementation of a quick convection scheme. What I'm doing here is I'm summarizing all the convection schemes in a single slide for your ready reference. So here my phi f is always phi u. Here in central difference scheme, which is linear interpolation, phi f is phi u plus phi d divided by 2. In case of a second order of wind scheme, it is phi f is equal to 3 phi u minus phi u divided by 2. And in case of a quick convection scheme, it is 3 phi d plus 6 phi u minus phi u divided by 8. This is quadratic convection scheme. Is there any question? I will take a question quickly if there are. Am I going ahead properly? Is higher order scheme always better? Yes, we are going to talk about the, the effectiveness of the scheme as we go ahead. Yes, higher order schemes are always better, but then there is a cost for that. When you implement the higher order schemes, your computational time is of course there, and your the level of complexity increases in the coding also. Is there any question? I hope my audio and audio, video, and the PPT is very clearly visible to all of you. Okay. Let's go ahead with the implementation part further. I'll be talking about the consistent implementation of higher order convection scheme, that is SOU and quick. Cell. This is our cell, which is controlled by the red line there. I mean, so far, whatever expressions which we have seen are applicable to pure interior cells. Expressions of the convection schemes, expressions to determine the value of variable on the however, when there is a border control volume, the distances are different. So the boundary conditions changes, and we need to modify the expressions for convection schemes. If it is a first order convection scheme, the expression will be same. That is, this value will be assigned to the phase. If it is central difference scheme, the difference between the average of this value and this value can be taken. However, if it is a second order or quick convection scheme, this distance is now different. It is half of that of delta x. When it was a pure interior cell, it was delta x. Now it is half of delta x. So this change in the geometric parameter is to be incorporated in the development of an expression for determining value of phi. So now here, this is my phi u. This was the earlier case. If this is phi e, this is phi u, phi u. But now, in the current case, if this is my east phase, this is phi u, and this is phi b, which is phi u. This boundary value of phi b. If I incorporate this, the expression for phi e changes to 2 phi u minus phi u. And the expression for quick convection scheme changes to 1/3 of phi d plus phi u minus 1/3 of phi u. So these are different expressions which we can obtain. We can obtain these expressions in the same fashion as we obtained it for the earlier cases. You can do that yourself. I mean, this derivation is very simple. You quickly can understand and do that. So for border control volume, you need to take special care to obtain the value of variable on the faces. If it is a left boundary border, if it is a border control volume, you need to obtain it for the east face. If it is the right border control volume, you need to obtain it for the west face, and so on, so for north and south faces as well. So these expressions you need to obtain carefully to determine the value of phi. Now let us come to the solution part of it. Uh, we have implemented these convection schemes for the problem which we have talked at the beginning itself. There is an oblique flow occurring over the domain. In the domain, uh, this oblique flow can be resolved into two components, that is u velocity and v velocity. And these u velocities and v velocities are convecting. These are convecting variables, and these are convecting some variable which is called phi, and that phi is being convected, and its value on this boundary is 1, value on this boundary is 1, here it is 0, and here it is 0. So phi is being convected. How will it be convected? How the distribution will look like? That's what we want to understand. So our objective is to find out the variation of phi as a function of x and y. So governing equation for, if it is a 2D steady state convection, the governing equation is divergence of rho u vector phi is equal to 0. And the finite volume discretization of this quantity is summation or east, west, north, south faces of summation of FMF phi f normal delta SF, that is equal to 0. This quantity is nothing but my convection flux, and if I multiply it by area, I get total convection. So Cp phi is equal to 0 is the governing equation. This total quantity is nothing but the total convection which is occurring across all the four faces, that is east, west, north, south. In that situation, I am providing you here with the simple equations for all the convection schemes, which you can use for doing some manual calculations of the variable. And when you use your actual code, you can verify whether the results obtained manually and results obtained through the coding are same or not. For example, if I take a FOU's convection scheme, for FOU convection scheme, my phi E will be phi P. Phi W will be phi capital W. Phi N will be phi P. And phi small s will be phi S. That's written here. For central difference convection scheme, if it is phi E, it will be phi P plus phi E divided by 2. Phi W, it will be phi capital W, phi capital P divided by 2. Phi N, it will be phi N plus phi P divided by 2. For phi S, it will be phi P plus phi S divided by 2. These expressions are written here. If it is a SOU convection scheme, if it is phi E, then my expression will be 3 phi P plus phi W divided by 2. If it is phi W, then it will be these two upstream values will be used. Phi W, 3 phi W minus phi W divided by 2. If I want to find it for north face, then it will be 3 phi P minus phi S divided by 2 here. And if I'm trying to find out for the south face, then it will be phi S, 3 phi S minus phi S divided by 2. So we are using two upstream values. Similarly, we can do write an expression for quick convection scheme. Phi small e, if it is. So I will be using this value, and this value. These expressions are provided to you for your easy understanding. And these are provided when my mass flux in x and y direction is positive. If it is negative, the expressions will be different. So phi e, if it is a convection scheme, so it will be 3 phi e plus 6 phi p minus phi w divided by 8. So phi E, phi P, and phi W is used. If I'm doing it for phi W west face, my phi P, phi W, and phi W will be used. Phi P, phi W, phi W will be used. If I'm doing it for north face, phi N, phi P, phi S will be used. Phi N, phi P, phi N. If I'm trying to find out the value of variable on the south face, it will be phi P, phi S, and phi SS will be used. So these are the equations which can be readily used readily. So if it is a 2D steady state convection, pure convection equation, my summation over Fm F phi Fn delta SF, this is my total convection, will be equal to summation over east, west, north, south faces of phi F delta F is equal to 0. What is done here? Uh, if I look at the equations carefully here, I mean I can write down this equation now because this quantity is all equal to 0, because this FMF is not 0 in this quantity, because my mass flux cannot be 0, the summation of rest of the quantity is equal to 0. So this equation instead of equal to sign, I should have put it here. This equation employs that summation over east, west, north, south faces of phi F at nth time instant, phi F in the normal direction into delta SF is equal to 0. So now I can write it for eastern north faces and west and south faces. Eastern for north, why I'm disintegrating this like this? Because for east and north it is positive, and for west and south it is negative. If I use first order convection scheme, my phi P will be, I mean, if I put the expression for phi F with the help of FOU here and here, I will have the quantities like, see here, my phi E is phi capital P, phi W is phi capital W, phi N is phi capital P. So I will be having two phi P's in the expression, right? So two phi P's, if I take two onto that side, and I will be having one phi W and one phi E. So if I put the value of phi F here using first order of wind scheme, for east face it will be, for east face it is phi P, for west north face it is again phi P, for west face it is phi capital W, and for south face it is phi capital S. So if I put those values here, I can find out the expression for phi P, which I need to determine. So phi P will be phi W plus phi S divided by 2. Similarly, I can do it for the central difference scheme. For central difference scheme, phi F is, so that is phi E is, sorry, phi E is phi capital E plus phi capital P divided by 2. I can write down for north face, south, west face, south face from the central difference scheme, and then I can obtain the expression for phi P. And if I put it like this, I can obtain the expression for phi P, which I have not written here, but I can do that. Similarly, I can do it for second order of wind scheme and quick convection scheme. So we obtain expression something like this for the various values of phi P. So these values of phi P's can be determined for all the cell centers. So these are the new values of phi P's, which will provide us the convected variable in the entire domain. So what we can do, we can deploy these equations, we can deploy these equations to all the cell centers and find out the new values of phi P. And then we can iteratively find out newer and newer values. We can go ahead with some initial guess, we can find out new value of phi P. either using FOU, SOU, CD, or quick convection schemes. This problem is being looked at. So, I mean, we can find out the steady stress. I am going to share the solution with you as I proceed. First, look at if the process is unsteady, how the equations will change. If the convection is unsteady, then this is my governing equation. I have already uh, obtained the expression for the unsteady term, and this is the expression for the convection term. When I write down this convection term at nth level, then the solution method becomes explicit. If I write down it at n+1 level, it becomes implicit. We have already seen what is explicit and implicit. So from my, if this is the, if I'm using an explicit method, then I need to calculate the value of a variable on the faces using current values. So all the current values are known to me from either initial guess or initial condition. Especially in a steady state problem, it is initial condition. So I can calculate phi f values from initial conditions. FMF is known to me, delta SF is known to me from grid generation. So only unknown left is phi p at next level. So which I'll find out, and I can scroll through all the cell centers and I can find out it for all the cell centers. So that will be the that will represent the value of phi p at new time instant. Delta t, of course, there is a limitation if I am using an explicit method. I will talk about that in the next slide. But if I write down this phi f is of course required to be determined using convection scheme. If I write down this phi f using next level values, then this phi f cannot be determined. But if I write down such an equation for all the cell centers, I will have as many equations as the cell centers are there, and I will have as many unknowns as the cell centers are there. So as many equations, so number of equations and number of unknowns will be equal, and those equations can be then solved simultaneously, and such a method is called implicit method. So there are two ways to obtain solution to unsteady state problem, implicit and explicit. For explicit problem, we have a stability criteria, as in the case of earlier case also we have seen. There is a stability criteria for for conduction problem also. This stability criteria is called Courant-Friedrich-Levy criteria. It is delta t into mod of uij upon delta x plus mod of vij upon delta y should be less than equal to 1. If this is followed, then only my solution will be converged. Else my solution will diverge if I am using explicit method. We have already seen the advantages and disadvantages of explicit and implicit method. I need not to go through that again. So from this equation, I can always calculate delta t, and I can make use of that delta t in this expression to obtain the solution for phi p. The new value of phi p. I can quickly go through the solution algorithm. The solution algorithm is along the same lines as we did it in the last session. Enter all the inputs, geometric properties, L1, L2, maximum number of control volumes in x and y direction, boundary condition inputs, and epsilon value. This is for the convergence. We have discussed it yesterday. We have to do the grid generation to calculate all the geometric parameters. We can set delta t from stability criteria. Now the stability criteria is different, so I can use this expression delta t is equal to 1 upon maximum of this quantity and can determine delta t. Then we can calculate the mass fluxes FME, FMW, FMN, FMS, that is for all the phases. Then we can set the initial condition for phi ij. We can set the boundary condition for phi, which is given to you. Once done that, what we do, we assign all phi ij. All these phi ij's are known to me either from initial condition or boundary condition. I assign all these phi ij's to phi 1, which is another variable which we have. Then what we do, we use the convection scheme to calculate phi f, and then calculate the total convection at the cell centers, at all the cell centers using CI. Cij is FME, FF, phi E, FMN, phi N. These are to be determined. These are values are to be determined from the convection schemes. and we know the convection scheme. So once I know Cij, explicitly I can write down the solution for new value of phi ij as phi old ij minus delta t upon rho Vij to Cij. This is the expression which I'm using. This is my new, this is old. This is Cpij. This is Cpij. I take it onto other side. And then Cpij will be multiplied by delta t and it will be divided by rho and delta Vp. And this quantity, when I take onto other side, will become positive. So this old quantity is positive. So the same thing is this old quantity is positive, and then Cpij is a negative, but it is multiplied by delta t and divided by rho delta Vij. So I can find out new value of Vij. Then I can check for the convergence using RMS value of phi. If this convergence with this RMS value is less than epsilon, then my solution is converge, else I need to go back to step number 7 and again continue and do the iterations to obtain the convergence. Once the convergence is obtained, you can write down you can print the values of x, y, that is coordinate x and y coordinates, and the value of phi, and then that value of phi can be plotted. Here I'm just sharing with you the solution we obtained using different convection schemes. Because we have not implemented the central difference scheme, but we can at least look at how the solution looks like when I implement solution for first order, second order, and quick convection scheme. For such kind of a problem, why we did select such kind of a problem? Because there is an exact solution available for such kind of a problem. So this is essentially the what I am showing you here is the variation of phi along the vertical y direction. It's a where variation of phi along the vertical center line. This is the problem. I'm just considering a vertical center line, and I'm trying to plot the value of phi along the vertical center line. So this is one boundary condition is 1 here, 0 here, and 0 here. And u and v are known to me, and I am trying to now obtain the expression for, I am trying to obtain the values of phi in the entire domain. From that entire domain, I have just extracted the data for phi along the vertical direction. That has been plotted here. The grid size is 22 by 22. You can see my FOU convection scheme. The results are shown by red line. SOU is shown by green, and quick is shown by blue. The exact solution is by black line. You can see the quick convection scheme gives me the solution which oscillates far away from that of the exact solution when my grid size is 22 by 22. But the moment I refine my grid size, when I make it 52 by 52, my quick convection gives me a solution which is very close to that of the exact solution. But first order of wind scheme, even with higher grid size, does not give me solution which is close to the exact solution. So this is what I do have for the pure convection. We'll be discussing few more things when we will be actually going ahead with the convection diffusion problem. If you have any questions, please go ahead. I'll be happy to answer your questions. Thank you very much for your patience listening. Please, participants, go ahead with the questions if you have. Is there any question? Am I audible or not?
Audible, sir. Thank you, sir.
Yes, sir.
Yeah, Professor. Do you have a question? Tumbanath, no? Professor Tumbanath?
Sir, no, sir, no, sir.
Either I have explained everything nicely, or I mean you could not understand anything. So two possibilities if you are not asking any of the questions. Okay. Why phi changes at the center portion? Exact solution. It's changed because it is being convected. It changes along the. See, you just have a look at the physical problem and look at the boundary conditions. This along this direction, I have plotted the phi value. So my phi is bound to be larger in this region. So it is changing in the central region only. See, the phi is 1 here, phi is 1. So this phi is being convected. This phi is being not, this phi is 0. The phi value is 0 here. So convection is more from this end. So the value looks like that. This is y is equal to 0.5. This region, the phi is changing from almost 0 to 1. And that's obvious result. Thus, I can say that my convection scheme is working well for the, and I can say my finite volume method is working well for the problem. Is there any other question? In the graph sharp at 0.4, why? The graph, it is sharp at 0.4. No, this is at 0.5. That's the center, no? That's the center. I mean, that's the physical nature of the problem. If you look at the physical nature of the problem, you will find that there's a sharp change at the center itself. Is there any question by the participant? Phi is not bounded in quick. Not bounded in the quick means it grows above 1 and 0. Yeah, that's a small variation we do obtain. I mean, this is a numerical solution, so we cannot expect the solution to be exact. So there is little bit of variation in the solution. If I make this grid size maybe finer, maybe I will be able to obtain the solution, very close solution in this region as well. But yes, you are true. We need to check whether with 101 if I am able to obtain the solution which is very close to that of the exact solution. But it is really not possible for numericals. I mean, numerical solutions cannot provide you the solution which is exact. Yes, you yourself has given. I mean, Professor Rana Robo has given the same answer. Further increasing the grid size, we get the solution identical to exact solution, or it remains as low. Now, with the further refinement, we may get the solution which is very close to exact solution, but it's not possible to obtain the exact solution. Is there any question? If there are no questions, then we shall stop for maybe half an hour, and we'll come back at sharp at 12 o'clock, and we'll go ahead with the next session. Thank you very much. I shall stop for